Hi, I'm Herb Gross, and welcome to lecture number 39 in our series Gateways to Algebra, where today we're going to try to capture the elusive square root of -1. Today we are going to solve the equation x squared plus 1 equals 0. Now remember, we already know that that solution cannot be what we've sort of arbitrarily called the real number system. We simply assumed at that particular point in time that we had exhausted all the possible numbers. It never occurred to us that there might be an application later on where it was important to go beyond what we were then calling the real numbers. I don't know if I've mentioned this to you earlier, but in a similar way, the ancient Greeks visualized numbers as being lengths. And so the shortest length they could visualize would be no length at all, you see. So therefore, if they saw a negative number, say -2, they would call that number imaginary. See, they hadn't invented negative numbers yet. And what they say is, how could a length be so short that if it was 2 inches longer, you still couldn't see it? See, realness, again, is in the eyes of the beholder. But anyway, let's go on with our quest and take a look at what we've done so far. See, so far, and let's just recapitulate here. With this, see, up until recently in this course, our whole life, mathematical life, was restricted to this narrow bandwidth called the x-axis. We had no idea of anything lying beyond this, sort of like a mathematical Star Trek. We suddenly discovered there's life out here. We can name points out here. Cartesian coordinates, the point A, comma B. And what did that mean now? Instead of looking at just the point A, comma B, we can think of it as what? The endpoint of a vector that started at the origin and went to the point P. And we could read that, the number P, as what? The number A plus BI, where A was the real number distance from here to here, and B was the real number distance from here to here. And by the way, what we also did was, the x-axis, in deference to historically what it meant, was then called the real axis, and in deference to remembering that we called these imaginary before, the y-axis entry is called the imaginary axis. So you have what? A real axis and an imaginary axis. Notice that physically they're both real, they're all over here. And what we do is what? We can locate any complex number by giving what? Its real part and its imaginary part. And we write it in the form A plus BI, where A and B are the real part and the imaginary part of the complex number. By the way, B is a real number, but it's called the imaginary part, meaning it's the adjective that modifies I. And in polar form, it would be what? The distance from O to P is R, and the angle is theta. And this whole thing together is given the name the complex numbers. And so again, by way of review, in Cartesian form, a complex number has the form A plus BI, where A is called the real part, B is called the imaginary part. In polar form, we measure what? The distance of the point from the origin and the direction that the line from the origin to the point makes with the positive x-axis. And how did we agree to multiply complex numbers? We simply agreed what? To multiply the two magnitudes and to add the two angles. So for example, 2, 30 degrees multiplied by 3, 40 degrees would be what? 2 times 3 is 6. 30 degrees plus 40 degrees is 70 degrees. So that would be 6, 70 degrees. And now we're going to discover the miracle of I, in this sense. I is the number what? 1, 90 degrees. Let's square I. What does squaring mean? It means to multiply by itself. So if I is 1, 90 degrees, what is I squared? It's 1, 90 degrees times 1, 90 degrees. How do we multiply? We multiply the two magnitudes. 1 times 1 is 1. 90 degrees plus 90 degrees is 180 degrees. Therefore, based on this definition of multiplication, I squared must be -1. By the way, just a little point here. I don't want to make too big an issue over this, but in mathematics, it's kind of crucial. You see, technically speaking, the number -1 doesn't exist in complex numbers. You see, -1 would be written how? It would either be written as -1 plus 0i in Cartesian form, or 1, 180 degrees in polar form. But since in spirit either of these two forms names the number -1, we don't really care which form we use. In other words, the logician would be very, very concerned about this. But as far as we're concerned, we're saying something like, hey, if a guy changes his name, he's still the same person. See, if there's 15 people in the room and you know all of them, and all 15 change their name, it's still what? The same 15 people as far as what? Their properties and their habits are concerned. And that's basically the attitude we're going to use here. That technically speaking, you have to use the new language, but in the part where the new numbers are the same as what we had before, we'll keep the old names because we're familiar with them, okay? Just a little word that way. So anyway, what happens now when you multiply by I? It appears that I multiplied by itself gives you -1, okay? And by the way, it doesn't really matter what number. Suppose I took 2, 30 degrees and multiplied that by I. I is 1, 90 degrees, isn't it? The 2 times 1 gives me 2. The 30 plus the 90 would give me 120. And notice that what happened over here is that multiplying by I didn't change how far away this number was from the origin, but what did it do? It added 90 degrees onto the angle. In other words, multiplying by I gave me a 90-degree rotation of the plane. In other words, what happened was things were rotating. It wasn't just that I multiplied by itself gave me -1, but what happens when I multiply -1 by I? If I multiply -1 by I, what happens? -1 is 1, 180. Multiply that by I. 1 times 1 is 1. And 180 plus 90 is 270. Didn't that just rotate again? And by the way, what name should we give this? If this number here is I, what number is this one down here? Well, doesn't this line here have the same length as this one? Doesn't it have the same direction? All it has is the opposite sense. In other words, the arrowhead direction is reversed. That's exactly what you mean by the negative of a vector. In other words, if I take a vector A, and then starting at the head of A, I lay A off right along itself till I come back to the tail, isn't that going to give me a 0 vector from the tail of the first to the head of the second? In other words, a vector that has the same direction, the same magnitude, but the opposite sense of a given vector is the negative of that vector. I just want you to see that in general. In other words, here's the vector OP. If I now draw a straight line through O that's a continuation of OP, but in the opposite direction, and I make sure that the point Q is the same distance from O that the point P was, then the vector from O to Q is simply the negative of the vector from O to P. And with that in mind, you see, if this complex number here is called I, what would this complex number here be called? It would be called -I. So I is 1, 90 degrees. Negative I is 1, 270 degrees. And by the way, when we were dealing with real numbers, wasn't it true that if you squared a real number, the sign didn't make any difference? I want to show you the same thing is going to be true over here. See, what was I squared? We just showed that was -1. Now I'm going to show you that if you square -I, the answer is also -1. Now what is -I? It's 1, 270 degrees. So to square it means what? Multiply it by itself. Well, the 1 times 1 gives me 1. What's 270 plus 270? It's 540. But the circle only has 360 degrees, doesn't it? So if I subtract the 360 from the 540, that's 180 degrees. And what that says is what? When you square -I, where does it wind up? Technically speaking, it's at the point 1, 540 degrees. But what does that point look like? 1, 180 degrees, and that's precisely what -1 is. So in other words, if we now define the complex numbers to be the set of all numbers of the form a plus bi, where a and b are real numbers, then the equation x equals x squared plus 1, x equals x squared plus 1 equals 0. The set of all x such that x squared plus 1 equals 0, what's the solution set to that equation? 1 and, I and -I, or as we write it, plus or minus the square root of I. And remember, in this particular situation, what's happening over here? I is simply an abbreviation for 0 plus 1i. In fact, see, the set C is called the complex numbers. All complex numbers have what form? a plus bi. Now, a number is real if the imaginary part is 0. See, if b is 0, then all you have is what? The a over here, and we just leave this part out. If the a part is 0, then all we have is what? A multiple of I. See, so the x-axis is called the real axis, the y-axis is called the purely imaginary axis, and any number that combines a real number with a purely imaginary number, see, that's called a complex number. And just as an aside, let me show you one more thing over here. What's really neat about the number I is that no matter what power you raise it to, it's either going to come out to, no matter what power I is, no matter what power you raise it to, the answer will either be plus or minus 1 or plus or minus I, depending on what n is. And let's see why. See, any number to the 0 power is 1. I to the first power, by definition, is still I. I squared, we already saw, was negative 1. I to the third power is what? I squared times I to the first power. See, all these rules still apply. We're assuming in this extended system we don't change the rules that we already have. But I squared is negative 1, so I to the third power is negative 1 times I. And what's the power of negative 1? What's the property of it? It changes the sign. So negative 1 times I is negative I. Now what's I to the fourth power? Well, you could say it's I times I to the third power. I think an easier way would be to say what? It's I squared times I squared. I squared is negative 1, so I to the fourth power is negative 1 times negative 1. That's positive 1. And look what happens. See, if I now have I to the fifth power, isn't that I to the fourth power times I? But I to the fourth power is 1, so I to the fifth power brings you back to what? 1 again. In other words, every time you go through the fourth power of I, you're back to 1. And what this does is it shows us that we never have to deal that much with anything other than ones and i's. See, for example, if I raise I to the 142nd power, every fourth power is going to give me 1 again. So all I do is look at the remainder when the exponent is divided by 4. See, my claim is this. 4 goes, not my claim, we can see this. 4 goes into 142 35 times with a remainder of 2. Therefore, I claim right away that I to the 142nd power must be the same as I to the second power, and that, of course, is negative 1. Now, how did I know that? Well, see, what I just showed you over here was that 142 can be written as what? 4 times 35 plus 2. Well, I to the sum of 2 powers, remember, when you multiply like bases, you add the powers. So this can be rewritten as what? This is I to the 4 times 35 times I to the second power. Grouping this way, I to the fourth is 1. 1 to the 35th power is still 1. So the answer to this problem is the same as what? I squared, which is negative 1. But again, just by way of review again, remember what we said now. What's important about the number I? It's not just that I squared is 1. It's that what? Multiplying by I rotates the xy plane by 90 degrees. In other words, let's review again. If r comma theta equals r comma theta times I is what? R comma theta times 1 plus 90 degrees. R times 1 gives you r. Theta plus 90 degrees is theta plus 90 degrees. And how is an angle and the angle plus 90 degrees related? It just means you rotate that angle through 90 degrees. For example, suppose r comma theta was suppose this was the point P. So r is now what? 2, and theta is 27. If I multiply that by 1 comma 90, the 2 times 1 gives me 2. By the way, what that says is, at the point O, if I drew a circle of radius 2, the product of of P and I would still be on this circle. What would the angle be? It would be this angle plus 90 degrees. Hasn't that, in effect, rotated the whole plane through 90 degrees? See, every point gets rotated through 90 degrees. And in fact, there's nothing sacred about rotating the plane through 90 degrees. Look, let's suppose I was graphing something, and just by some crazy coincidence, this is beyond where we are in the course, suppose I wound up with a parabola that looked like this. In other words, the axis of symmetry was this line rather than the x or the y axis. Can you see what bothers me about that? if I look at the graph this way, can you see that for a given x value, I can get two y values? This thing is off-centered. What I really would like to do is, since this is the axis of symmetry, I would have liked it better if the x-axis was over here, wouldn't I? See, in other words, if this had been the x-axis and this had been the y-axis, wouldn't this now look like a regular parabola, one that we're already used to? But the point is, how can I transform this picture into this one? And the answer is, whatever this angle is, call it d degrees. What I want to do is what? Multiply each point in the plane by 1 comma d degrees. Why is that? Because to rotate the plane through d degrees, you multiply each point by 1 comma d degrees. Why does that work? R comma theta times 1 comma d. The r times 1 gives me r. The theta plus d gives me theta plus d. That's my 90-degree rotation. So many, many times in mathematics, what we often do is we may rotate something to make it look more like this. Once we've rotated it, we may raise it or lower it to make it look more like this. See, basically, to look at this from a different point of view, it's much easier to move the axis than it is to move the curve. See, suppose I have a coordinate system that looks like this, and the picture looks like this. See, what I may want to say is what? Let me rotate my coordinate system so the axis of symmetry will be one of my new directions over here. See, so I want to rotate the coordinate system. I also want this to come down to here so I can get the form y equals x squared. So what am I going to do? I'm going to basically translate. I'm going to lower this graph. What does that mean? Plus or minus c. And just bring it down here. In other words, in terms of a picture, what I'm doing is what? I rotate this thing till it's perpendicular. Once it's perpendicular, I slide it up and down to the left and to the right until I finally wind up with what? A picture that looks very convenient for me. These are called transformations. And this is a very neat thing that we do in mathematics. A transformation is what allows you to take a problem that's fairly complicated and transform it into a problem that's equivalent, but you know how to handle that. If you want to see a non-mathematical example of that, I can illustrate that for you in terms of language. When you're learning a foreign language and you're not comfortable with it, when somebody asks you a question in the foreign language, what do you usually do? You translate it into your own language. Then once you're thinking in your own language, you answer it in your own language. And then you translate the answer back into the original language, don't you? Well, you see, that's a transformation. You transform the question from the foreign language into your own language, and in that domain where you were more comfortable, you solve the problem. And after you solve the problem, you transform the answer back into the original domain. And we do that very, very often in mathematics. If the problem looks too complicated, we try to do what? Alter the domain and solve the problem in the easier domain. But that's just a philosophical point that I wanted to mention to you, because it is a very, very important learning thing. But now, let me just go on with what we're doing over here. I do want to teach you one more aside, because we haven't done that much with geometry in this course. There is something I want to use for my next illustration. And I thought that what I'd like to do there is I would like you to know that in a triangle, the three angles, when you add up their measures, always will add up to 180 degrees. And the easiest way to prove that is, suppose you have any triangle. Let's call AB the base. And these lines over here name the angles. See, the one line names this angle, 2 lines names this angle, 3 lines names this angle. I claim that these 3 angles add up to 180 degrees. And the easiest way to prove that is through the point C, draw a line parallel to AB, a line that has the same direction as AB. See what's going to happen over here? Because these 2 lines are parallel, this angle here is going to be the same as this angle here. And this angle here is going to be the same as this angle here. Now, this angle plus this angle plus this angle is obviously the same measure as this angle plus this angle plus this angle, because you can see that these are the same angles. But how do these 3 angles here add up? Don't they form a straight line? And a straight line is what? 180 degrees. See, the reason I mention that is I want to now show you that it doesn't make any difference whether you solve a problem geometrically or whether you solve it algebraically. For example, let's take the complex number 1 plus I. What does that mean now? It means that the x component is 1 and that the I component is 1. It means that see, this is 1 plus 1i. That puts you at the point 1 comma 1, doesn't it? Now, another way of naming that number is in polar coordinates. Now, if this is 1 and this is 1, the Pythagorean theorem, if I call this h, tells me that h squared is 1 squared plus 1 squared. That says that h squared is 2. That tells me that h must be the square root of 2. So my r distance is now the square root of 2. The reason I did this other thing for you is I now want to figure out what this angle is. And what I wanted to show you is that this angle has to be 45 degrees. How do I know that? By the symmetry of this figure, this angle and this angle are equal, aren't they? This is a 90-degree angle because it's a square corner. The angles have to add up to 180 degrees. If this one is 90 and all three of them have to add up to 180, these two together must add up to 90. And if they're equal, each one must be 45 degrees. Therefore, another way of naming the point P is not just 1 comma 1, it's what? The square root of 2 comma 45 degrees. Now what I'd like to do is I would like to square this number two ways. The first way is the way that we would do this if we were looking at the complex numbers as being an extension of the real numbers. Didn't we already learn the formula for squaring the sum of two numbers? Wasn't it the first number squared plus twice the product of these two numbers plus the square of the second number? So this would be what? 1 squared plus 2 times 1 times I plus I squared. In other words, we want this rule to still be true. Now what happens? 1 squared is 1, 2 times 1 is 2, times I is 2i, and I squared is negative 1. The 1 and the negative 1 drop out. So if I square 1 plus I this way, what do I get? 2i for the answer. What happens if I use this form? The square of the number in polar form means what? It's square root of 2 comma 45 degrees multiplied by square root of 2 comma 45 degrees. I multiply the two magnitudes. The square root of 2 times the square root of 2 is 2, okay? And 45 degrees plus 45 degrees is 90 degrees. So now the answer is what? 2 comma 90 degrees. What is 2i, first of all? It's the number in the I direction. See, it's 0, see, no real part, and 2 the imaginary part. 2i means what? 2 units in the direction of I. On the other hand, what's 2 comma 90? It's the number you get by taking a 90-degree rotation and then marking off 2 units. In other words, either way, this number here and this number here are 2 different ways of representing the same number. The reason I like the polar form is this method works very, very nicely as an extension of our rules of algebra, but it's kind of hollow. There's no intuition about this. What's really nice about this method is you can see geometrically what's happening. See, what you've really done is what? You've taken this complex number and you've done what? Doubled the angle and squared its magnitude. And by the way, this works all the time. If I say to you, how much is 2 plus 3i times 4 plus 5i, see, I can graph them this way. You say, oh, this is going to be a mess to do geometrically. I'm going to have to add this and multiply their magnitudes. No, you can visualize it that way, but what you're going to do is what? Use the same rule of FOIL that we did in algebra. The 2 has to multiply the 4. The 2 has to multiply the 5i. The 3i has to multiply the 4. The 3i has to multiply the 5i. You wind up with what? 2 times 4, which is 8. 2 times 5i, which is 10i. 3i times 4, which is 12i. 3i times 5i, which is 15i squared. I squared is negative 1, so 15i squared is negative 15. What do we wind up with? 8 plus negative 15 is negative 7. 10i plus 12i is positive 22i. Therefore, what's the answer to this problem? It's negative 7 plus 22i. By the way, if I didn't know what this number is, in terms of division, shouldn't 7 plus 22i over 2 plus 3i, see this divided by this, give me this number over here? In other words, what I'd like to show is what? That if I take this number here and divide it by this number here, I get 2 plus 3i. I want to just show you how the same arithmetic that we've always used still works over here. See, the problem is I want to get this into the form a plus bi. A very interesting trick when you're dealing with these numbers is to notice that if you take any complex number, say a plus bi, and just multiply it by a minus bi, that's always going to be a non-negative number. Look why. Isn't this a sum and difference of the same two numbers? A times a is a squared. Positive bi times negative bi is negative b squared I squared. But I squared is negative 1, and multiplying b squared by negative 1 makes this positive. So if I multiply a plus bi by a minus bi, I get a squared plus b squared. A and b are real numbers, so a squared is at least as big as 0. B squared is at least as big as 0. So what's happened is my denominator is going to become a real number. See, I'm going to take 2 plus 3i, multiply it by 2 minus 3i. Just like with regular fractions, if I multiply the denominator by something, I have to multiply the numerator by the same thing. If I now multiply this out, the negative 7 times 2 gives me negative 14. The negative 7 times negative 3i gives me positive 21i. The 22i times 2 gives me 44i. The 22i times negative 3i gives me negative 66i squared. And down below I get what? 4 times negative 9i squared. Now look at, I squared is negative 1. Negative 1 times negative 66 is positive 66. What do I have here? Negative 14 plus 66, which is 52. 21i plus 44i, which is 65i. And I squared is negative 1. That makes this 4 plus 9, which is 13. Break this down into 52 over 13 plus 65i over 13. 52 over 13 is 4. 65i over 13 is 5i. There's the answer that we wanted. Now again, this is not meant to be complete and for you to understand all of this, but you start to get the flavor of what it means to extend a number system. Are you starting to get the flavor of the fact that the complex numbers are just as real as the real numbers and have just as many practical applications? But at any rate, we will conclude our course with the next lecture. But for now, continue to study hard, have fun, stay young. See you next time.